So hello guys, today we are going to discuss this problem combinations. So the problem goes like this, that we are given two integers n and k, and we have to return the all possible combinations of k numbers chosen from range from 1 to n, and we may return answer in any order. For example, for n equal to 4 and k equal to 2, let me go to auto draw. For n equal to 4, k equal to 2, we have a number from 1 to 4, that is 1 2 3 and 4, and we have to take two numbers at a time. So what numbers, two numbers we can take? Fixing 1 we can have 1 2, fixing 1 we can have 1 3, fixing 1 we can have 1 4. Then we move on to number 2, this one, and then we fix number 2, so we'll have 2 3 and 2 4. And then we move on to number 3, we can have 3 4. So we have six possible combinations. 4 and 1 will be equal to 1 and 4. So how we are going to do this? So in this question, we can see that we have to look at all the possible combinations or pairs, two pairs of a number. So whenever we have to traverse through all the possible combinations, we have to follow a method called backtracking. So this is a backtracking problem. In backtracking, what we'll do, we will move to 1. So okay, so before going on to uh, so basically, okay, I'll tell that what we do in backtracking is we will choose 1, then we will add second number to it, that is 1 and 2, and we will again jump to try to add the third number, that is 1 2 and 3. But we will find that the size should be 2, so we'll not add 3, and our let me delete it. And our this is 1 2 is our perfect combination, one combination we got it. Then what we do is we'll remove 2 from it, and we'll add another number to 1, which becomes 1 and 3. Then this subarray or the combination size becomes equal to 2, so we will remove 3 from it, that is we are doing pop back. We'll just see in code how we do pop back, removing the last dead entry, and we'll do 1 4. Now, similarly, we will move to number 2. So for number 2, the size is 1 for the subarray. We will add one more element in the subarray, and it will become 2 3. So we check that the size of subarray is equal to 2. So we'll not add more element, but we will pop back 3, and we will add one more element to this subarray, and it becomes 2 4. Then after 4 there are no elements. We'll move to element 3, and we'll add one element to 3. So when we move to 3, we'll check that the size of subarray is 2, so size of 3 is 1. So we'll add one more element, 4, and we will. So these are our six possible combinations. So how we actually perform a backtrack algorithm? Let me. So in main, this is a backtrack template which I'm going to tell you, which we can use in every backtrack problem. Take a candidate set. So candidate set is empty here. So candidates are this 1 2 1 3 1 4 2 3, right? And we take a start. So from which element we are going to find our candidate sets. And then we are going to call a recursive backtrack function with our candidate set and our start. So now let's go to our recursive backtrack function. We have our candidate set which is empty and start is 0. And then in we will write a base case here. I'll write the base case later. We will traverse for all the elements for I equal to 0, I equal to start rather, I smaller than n and plus plus I. That is, we are traversing to all the elements in the. Uh, so we'll start from 1, because why 1? Because we our elements are from 1, not 0. So I equal to 1, till I smaller than equal to 4, we will create a candidate set. So in first candidate set, we will add 1 here. And what we'll do, we will backtrack with start plus 1. So this will be the backtrack call, and we will do pop back from our candidate set. So this is only our logic. So let me go into the functions basically. So let's suppose we are on backtrack 1. Our candidate set is empty. So here what we in the for loop, we go into the for loop, and we find uh, we push first we push our element 1 into the candidate set, and we do 2 and candidate set 1. So we now jump to the backtrack 2 and candidate set 1. So now in backtrack 2 and candidate set 1, we again go into the for loop. I'll just tell about the base case later. And we'll put our second element, because now we are starting from 2, so 1 and 2, and we will do our backtrack 3 and 1 2. Now again we will go to the recursive backtrack, jump to the next recursive backtrack function 1 2, and here the base case will hit. So base case says, what base case is, it says if the candidate set size is equal to k, then we have to return from here. So now we return here, this function returns back, because our candidate size is 2 and k is also 2, so it returns back. And on the return back, what we have here is we have a pop back from candidate set. So when we do a pop back from the candidate set, it'll remove 2 from here. And in the for loop, as we remember, we were starting from 2 till 4. So now we'll get 3. So our um, backtrack function will become something like bt4 1 and 3, right? And now when it goes to this bt4 1 and 3, it will find that the candidate set size is equal to k. It'll come back and we'll note this 1 3 as well. So this is how we are going to find all the combinations. So let me just now quickly jump onto the code. Okay, so here we have the combine function. I have taken a constructor in which I have taken n, k, and candidate set. This is a list. So list is same as a vector in C++ and vector in Rust as well. And I have taken start as 1. So this is the recursive backtrack function. At start 1 and candidate set is empty at present. In backtrack function, this is the base case, which says that if the size of the candidate set is equal to 2, we are just going to append our output. This is our output array which we are going to return, this one, and we are going to return. So this is not the case in our initial, that is start equal to 1 and candidate set empty. So it will come here, it will append I, which is 1, and it will do a backtrack with I plus 1, that is it will do to 2, and then it will do a candidate.pop back, that is candidate.pop thing. And finally, we are going to return from 1 till end, because we are like having an empty vector in the double vector. So we are going to return from 1 to end, so slicing from 1 till end. So this is how we actually do a backtracking problem. So what will be the time complexity of this code? So time complexity in backtracking algorithms, and all the backtracking algorithms, uh, is the depth of the tree multiplied by the number of nodes on particular level. So as we can see, This is created as a tree, not as a binary tree, but as a tree, and we are doing a depth first search here. So whatever the depth of the tree here is, so at every level, at every node, we have only the depth as 1 and multiplied by the number of nodes at the level. So it will be 1, 2, and 3. So this will be 3, this will be 2, and this will be 1. So whole time complexity for this algorithm will be O6, and similarly the space complexity will also be O6 because at any point of time we'll have 6 recursive stacks. Rather it will be O3 because at any point of time, because when we will reach 2, that is when the candidate set becomes 2, it will come back. So at max 3 elements are possible uh, from there. So this is how we are going to solve these combinations and other related problems on the combination. Thank you. Have a good day.